Hey everyone, it's Dr. C. Thanks for a very nice first day of class. I thought we got a good start to the semester. We got a little bit of review done, and now this pre-lecture will kind of help us transition from Tuesday's lecture to Thursday's lecture. Now, when I originally started thinking about this lecture, I was going to use this pre-lecture to get into Chapter 18 material and get us started on that. And as I rethought that, I came to the conclusion it might be best to just wrap up the review material from Chapter 6 first, and then we'll jump into Chapter 18 on Thursday. So just to remind you of what we covered in class, we started talking about thermochemistry, heat flow and chemical reactions. Okay. Typically what we look at is something called the enthalpy change, which is the heat flow at constant pressure. And so we went through some problems in class, and so you can see the handout here. And if you were in class today, you should have this. All right. And we talked about the difference between an endothermic reaction and an exothermic reaction, systems, surroundings, things like that. So make sure you know the terminology. One thing that I didn't mention, we talked a lot about heat, but remember, heat energy is thermal energy. It's the energy of motion. It's a kinetic energy. So all atoms and molecules are in constant motion. Even solids, there's vibrations and things going on. So thermal energy, when we say heat flow, what we mean is thermal energy will flow, and that's kind of an interesting word, but from a substance at a higher temperature, because there will be more energy of motion in the substance at a higher temperature, to an object at a lower temperature where there's less kinetic energy, less thermal energy, less energy of motion. And eventually we'll reach an equilibrium where the thermal energies will be equal. But again, it's the flow transfer, let's use transfer rather than flow, transfer of thermal energy from a hotter object to a colder object. Okay? All right, so let's jump into this. And this is kind of an interesting question. And one thing to make sure you get out of this, phase changes can be a little tricky. So anytime we go from solid to liquid to gas, so that direction of phase change, okay? To melt a solid, we have to put in energy. We have to put in heat. To evaporate a liquid, we have to put in heat. We have to put in energy. So these are all going to be endothermic. And even, we could jump all the way from solid to gas. That's called sublimation. Same thing. Energy would have to be put in to do that. Now, remember, when we reverse the direction of a reaction, the sign changes. So if we go gas to liquid, condensation, okay, liquid to solid, okay, freezing, so let's just call it freezing. That's going to be opposite. That's going to be exo. Okay, we could even go gas to solid, which is called deposition. That's energy. We're going to have to, remember gas particles, for example, are moving very, very quickly, constant random motion, constantly colliding with each other, the walls of the container. We've got to pull that energy out of the gas, okay, that kinetic energy, so that the attractive forces of the liquid can take over so it can condense. Okay? And so we got to get energy out. Okay, so it has to be transferred from the system out to the surroundings. That is exothermic. All right. So for phase changes, a lot of times you have to think about the transfer of heat. What direction is it going? Is it going from the system to the surroundings, or is it going from the surroundings into the system? All right, enough with that. The other thing we did in class today, just to refresh, and we will get to some new stuff very quickly, make sure you realize it's a very important concept that a delta H that's given with the reaction is for that reaction as it's balanced. If we reverse the direction, the sign changes. This reaction is reversed and it's multiplied by 3, so the correct answer here was 3 times the negative of the delta H from that previous reaction. All right, because they are related, but remember the delta H is for that reaction as it's balanced. Very, very important. On the quiz that you're going to take after you watch this, there is one very, very similar to this, but it's slightly different, so read it carefully. It's not exactly the same, so read the question carefully. The next thing we did in class, along the same lines, again, this delta H that's given is for that reaction as it's balanced, And so this is the heat flow for 1 mole of methane. So 802.5 kilojoules of heat is released. Again, that negative sign tells us direction. Exothermic heat's released for 1 mole of methane reacting. If we react a different amount of heat is going to be released. In this case, that's 64.17 grams. We use the molar mass. Okay, dividing by the molar mass to find out how many moles of methane that is. I chose easy numbers for this problem so that it comes out to pretty much exactly 4 moles. So if 1 mole gives you so much heat, 4 moles is going to give you 4 times the amount of heat. Makes sense. Nothing tricky there. This is what I like to call stoichiometry for thermo. Okay, how does the mole ratio factor into the heat flow for a reaction? Now, very important, some of the problems you're going to get, the numbers are not going to be this nice. And you might have to set up a unit conversion like we did here. And we know, here's our conversion factor, 802.5 kilojoules per 1 mole. Now, if you did have a reaction where this coefficient was not 1, if it was 2 or 3 or 4, you'd have to factor that in. It might be, you might have a certain number of kilojoules per 3 moles of reactant. And so it'd be that many kilojoules per 3 moles. But anyway, you set up a conversion factor, 4 moles times that, moles cancel, and we end up with 3210 kilojoules. So sorry for the quick review. I know you were in class today, you're paying attention, but it's kind of just good to recap, make sure we're on the same page. Again, last thing for this problem, these are positive because that negative sign is just telling you direction of heat flow, system to surroundings. Energy is a positive quantity. All right, so the released word tells us direction. So it would not make sense to talk about a negative amount of energy released. That would make no sense. Okay? All right. Let's do a couple of new things for this pre-lecture. And let me go ahead and put this on this question on the next page so that it doesn't split like this. All right. So one thing that you should remember from last semester is that we looked at a variety of ways to calculate delta H. One was from delta H of formation values. We also used a process called Hess's law, where we took some known reactions and added them up to get the reaction we wanted. And we also used bond energies toward the end of the semester to estimate delta H. So the point is there are various ways for us to get to delta H. Let's focus on delta H formation values. And as we saw in class, let's first balance this reaction. Okay, propane is C3H8. I don't expect you to know that. You might. I would give that on an exam, so don't worry about that. You should know how to balance equations. Combustion reactions, reactions with oxygen gas. And if it is a compound containing only carbon, hydrogen, and or oxygen, what are your 2 products of that combustion? Now that's assuming complete combustion, that it's 100% efficient. What are our 2 products? I think you got this. Carbon dioxide and water. Now let's go ahead and put water in the vapor phase, because that's how it will initially be, because this reaction is going to produce quite a bit of heat, and so water initially will be in the gas phase. It will condense to a liquid as the reaction cools, but let's leave it in the gas phase for now. All right, balancing. 3 carbons, we need a 3 in front of CO2. 8 hydrogens, we need a 4 in front of water. 3 times 2 is 6 oxygens from the carbon dioxide. 4 times 1, 4 more, that's 10. Looks like we need a 5 there. That's very quick, but you should know how to do this already. All right, the way we use delta H of formation values, you probably remember this equation. To calculate the delta H of that reaction, we sum together the delta H of formation values of our products, and we subtract off the sum of the delta H of formation values of the reactants. All right, you will see this on the quiz, so make sure you know how to do this. Be very careful about this negative sign, and I will emphasize that when we get to it. So look up these values. The problem on the quiz, I put the values in it, so there's no discrepancy about what values to use. When you get to Alex problems, use the values that Alex has. All right, but for the quiz, there are values in the problem on the quiz, so use those. So let's look at some numbers. Carbon dioxide, look down here, minus 393.5. Water, be careful, make sure you have the right phase. We're going with water vapor here, so minus 241.8. And then we had propane gas, C3H8, negative 103.85. Okay, so watch your signs, make sure you have the correct sign for these values. So let's go ahead and plug these in, and we'll talk about oxygen in just a second. So we have 3 moles. Now don't forget, those delta H of formation values are per 1 mole of substance. By definition, that's what a delta H of formation value is. It's for the formation of 1 mole of that substance. We have 3 moles of CO2. The value for that was negative 393.5 kilojoules per mole. We are going to sum that to the other product. So that Greek letter sigma means take the sum. 4 moles. Water was negative 241.8 kilojoules per mole. And then we subtract off the sum of the reactants. Now our reactants, we only have 1 mole of propane, and that was negative 103.85. I hope that's right. Kilojoules per mole. I will double check that in just a second. And we have 5 moles of O2. Now, we could have looked that up in the table, but I expect you to know this. Oxygen gas, O2 gas, is an element in its most stable state. Okay, oxygen gas exists most stably as O2, and it's in the gas phase at room temperature. So what's its delta H of formation value? Yeah, I think you remember this. Elements in their standard state, their most stable state, are 0. Okay, so you should know that. All right, let me just double check the value for propane. I do not have that one memorized like CO2 and water. Yes, negative 103.85. All right, so let's punch these numbers into our calculator. So we're going to do 3 times 393.5. Make sure that's negative. 4 times 241.8. That's negative as well. And now here's where you need to be careful. We're subtracting off this negative number, so we have to add 103.85. And let's see here. So I think we have 1 digit after the decimal point to carry. So we have 1 digit here. Remember, when you add addition or subtraction, you look at the decimal point. We have 1 digit after in both those numbers. We have 2 here, so we carry the fewest. So it looks like here we should carry this as negative 2043.9 kilojoules. How's that look? Okay, hopefully that looks good. Negative sign, is that what you expect? Yeah, this is a combustion reaction. It's going to produce pretty good amount of heat. Combustion of propane. Some of you may have homes or live in an apartment or whatever where you use condensed propane to heat your home. Okay. Obviously, a lot of barbecue grills, those little propane cylinders, or campers or whatever. So this is exothermic, negative sign. This reaction is going to produce quite a bit of heat. All right, very good. Last thing for this pre-lecture, and again, it might be a little longer than I wanted. I think I'm at about 15 minutes. But this is just going to re-emphasize a very important concept. This is new here, using, not new, but reinforcing delta H formation to calculate the delta H. Again, That is for how this reaction is balanced. And we have a coefficient of 1 in front of propane. Well, what if we react a different amount of propane? Well, of course, we're going to get a different amount of heat released. All right, well, let's see how much that is. We're going to react 176 grams. So propane, let's get its molar mass. 3 carbons at 12.01 each. 8 hydrogens at 1.008 each. And I get 44, that's not a negative sign, 44.094 grams per mole for propane. We know the heat flow for 1 mole. We just figured that out in the problem before. How many moles is 176 grams? Okay. I will say this to you many times throughout the semester. Please write units. Students, for whatever reason, I lumped all students together. That's not very good to do. A lot of students don't like to write units. You will get yourself into trouble at some point in this semester if you don't write your units down. So please, please write units. And double check your units. All right, you should look at your units here and see grams in the numerator cancels with grams in the denominator so that you know that you didn't flip your molar mass. We want to divide by molar mass here to go from grams to moles. And this comes out to almost 4. I get 3 sig figs. I get 3.99 moles of propane because there are only 3 sig figs in 176. I'm going to keep the entire number in my calculator, and that's what you should do. It's actually 3.991. Let me get a couple more sig figs. 3.99147. So I'm going to leave that in my calculator when I go on to the next step. And the next step is we have 3.99 moles. We know, and I just scrolled it off the screen. I'm sorry. We really need to see that value. Let me go just a little bit more. 2043.9 kilojoules per 1 mole. And again, double check that coefficient. It is 1 in this case again, but you will have some reactions where the coefficient is not 1. So it'll be that many kilojoules per however many moles you have. Again, check your units, write your units down. And we only have 3 sig figs, so I'm going to have to write this in scientific notation. And the 3 sig figs in scientific notation, 8.16 times 10 to the 3rd kilojoules. Okay? And I apologize. Sometimes when I write problems, I don't think them through, and I just pick numbers. This one turned out to be 4 moles as well. That's not... it's not like we're always going to react 4 moles of substance, obviously, but they both worked out to be right about 4 moles. Released, how much heat is released? We don't. That's our sign. Our sign's taken care of. It is a positive amount of energy that is released. That negative sign for delta H is just telling us direction of heat flow. Okay, so watch for that. All right. I hope these pre-lectures help. I really like them. I'm going to try to record all of them live because I think it really helps us to communicate a little bit better. You know, we have a very large class, and sometimes it's difficult to cover everything in class and get things done, and sometimes I forget some things that I should talk about and whatnot. But this really helps us transition between classes. And in particular, Thursday to Tuesday is a big gap. Okay, we won't see each other for 5 days, although you might come to office hours or whatnot. But that's a big gap between classes, and so particularly that Thursday pre-lecture to lead into the next Tuesday is going to be very, very helpful. All right. So for the quiz is in Blackboard, just to give you a little heads up. It will cover this material that we've gone through. So make sure you know exothermic, endothermic, know the sign convention. Make sure you know how delta H is affected by multiplying by a factor or turning the reaction around. Make sure you can do a calculation like this one where you react a different amount of substance than what's in the balanced equation. Make sure you can do a problem where you calculate delta H of a reaction from delta H of formation. Watch that negative sign. You know, you are subtracting off the reactant, so you might have subtracting a negative number, so watch for that. Watch for elements in their standard state. Those will be 0 for delta H formation. Okay? I think that's most of what's on the quiz. There's no time limit on the quiz. When you open it up, it's just going to pop up these multiple choice questions. Take your time. Try to do really well on these. These are a pretty good chunk of your grade. They're 12.5%. All right, sorry for going a little bit longer than I wanted, but this is our first one. I want to try to keep these to about 15 minutes. This one's been right around 20-ish, but I'll give myself a little excuse for it being the first one. All right, I will see you in class on Thursday. Don't forget to get into ALEX. There's an assignment due Friday. Okay, and we'll talk more about ALEX in class on Thursday and give you just a little bit more information, particularly for those of you who haven't used it, and there are some of you in the class. All right, see you soon. Take care.